In the world of networking, we learn to think in layers. It's a fundamental skill, drilled into us from day one. On the screen of a packet capture tool like Wireshark, we can see the layers clearly. Layer 2, the data link layer. Layer 3, the network layer. Layer 4, the transport layer. The structure seems clear, but the more you look at this real-world data, a fundamental question emerges. If the OSI 7-layer model is our blueprint, then where is Layer 6? That question highlights a crucial distinction in networking, the difference between a conceptual model and a practical implementation. The 7-layer OSI model is a foundational concept. It's a powerful tool for teaching and understanding the complex functions of a network. It provides a universal language, allowing engineers all over the world to discuss network functions in a standardized way. However, it's important to understand that the OSI model is a theory, a blueprint for how a network could be organized. The internet that we use every day wasn't built strictly following this blueprint. It was built on a different, more practical model, TCP/IP. Today, we'll look at the evidence and understand why this distinction is so important. Let's examine the actual data from a simple web request. The evidence is in the packets themselves. We'll break down this packet, starting from the bottom, following the OSI model structure. First, the data link layer. We have our Ethernet header. It's here. Next, the network layer. Here's the IP header. Present. Then, the transport layer. The TCP header is right here, also present. So far, the packet structure aligns with the model. But now, let's look closer at what comes next. Directly after the transport layer, we find the HTTP protocol data. There is no separate header for the session layer, nor for the presentation layer. They simply aren't here as distinct entities. So, who's doing the job of the presentation layer, like handling data formats? It's the HTTP protocol itself. Headers like content type are performing that function. The roles of the top layers have been consolidated. This is the practical evidence of the TCP/IP model in action. What we've just observed is the structure of the TCP/IP model. It's not a theory, it's a description of the protocols that actually run the internet. Application layer. This is where HTTP lives. It combines the jobs of OSI's top 3 layers: application, presentation, and session. Transport layer. TCP and UDP provide reliable or fast delivery. Internet layer. IP handles the routing. Network access layer. Ethernet and Wi-Fi handle the physical transmission. This is the implementation that powers every website you visit. It's a more streamlined and practical approach. So, if the real world uses TCP/IP, what is the purpose of learning the OSI model so thoroughly? Because it remains an incredibly powerful tool for troubleshooting. When something breaks, the OSI model gives us a universal language and a systematic checklist. Is the cable plugged in? That's layer 1. Is the device getting an IP address? Layer 3. Can it form a TCP connection? Layer 4. It allows us to isolate problems with precision, regardless of the underlying technology. Ultimately, neither model is right or wrong. They simply serve different purposes. The OSI model is an essential framework for learning, communication, and troubleshooting. The TCP/IP model is the practical reality of how the internet is built. The key is to understand both. A great network engineer uses the OSI model as a universal language to diagnose problems, while understanding that the underlying structure is based on TCP IP. Knowing the difference between the blueprint and the building, that's what separates network engineers from network experts. Alright, what networking concept would you like a practical look at next? Drop your suggestions in the comments below.